today I'm going to be talking about modelling future coastal evolution and storm impacts on gravel barrier coasts. So the model that I'm working with, the model that I'm developing, is called Cove. So that's what I'll be talking to you about today. So I'm going to be talking about gravel coasts and why they're important, why we need to understand their evolution. I'm going to talk about development, and I'm going to talk about how we can use these types of models to feed into coastal management and coastal engineering to help policymakers make decisions about shoreline management for the future. So gravel barrier coasts. So this image comes from Fairbourne in North Wales. So gravel coasts essentially formed at the beginning of the Holocene. So as sea levels slowly started to rise, they would deliver lots and lots of offshore sediment to the shoreline, and over time they would just naturally accumulate and build up, and then you get these systems. So you find these systems in high latitude coastlines. They're very prominent. They account for 1,000 kilometres of the coastline of England and Wales, but you also find them in Canada, Argentina, New Zealand, etc. Why is Fairbourne unique? Well, Fairbourne is one of the first places in the UK where the shoreline management, so that's the advice to local councils about how to manage the coastline, is going to go to do nothing. So do nothing means you leave the coastline alone, you don't defend it, you don't protect it. So essentially that means that this entire village will get decommissioned, so everyone will have to move out, and it's basically just going to be left to sea. So in the meantime, we need to understand how the gravel system is going to evolve over sort of seasons to decadal timescales. And modelling of gravel barrier evolution lacks behind some of the modelling that we have for sand, because gravel behaves quite differently. It's got different density, it's got different porosity, and some of the modelling of those systems lacks. That's it. So this looks a bit technical, but I'll break it down. Cove is no, I won't. Cove is a one-line coastal evolution model. So these sorts of models make the assumption that you can represent the coastline using a single contour line. So if you look down the coastline has an equal elevation all the way along, and the bathymetry is depth parallel. So it looks like that. That's what your contour lines would look like. So in the top left, which one's the pointer? Top one. In the top left, we start offshore at the depth of closure. The depth of closure is the most offshore point at which the waves and the tides stop moving the sediment. So it's kind of where these models need to go to. And how they work is everything from that point, the depth of closure, to the coastline moves in equilibrium. So over time, you have an equilibrium shore face that progrades or erodes. Why is Cove unique to other models? Well, you can see here, other models would have this sort of grid system, and they would basically, they can only handle perfectly straight coastlines. As soon as you want to do anything technical, the old models wouldn't work very well, and this is where Cove came in. So Cove was originally written by one of my supervisors, and I won't go into the technical details, but essentially it allows you to handle very, very highly curved coastlines, and that's essential for management, because now coastal management's going towards trying to work with nature rather than sort of hard engineering structures. So you might have seen the sand engine in the Netherlands. It's just like a huge nourishment. Millions of tons of sand are put down, and you can let nature and waves move that system for you and protect the coast for you. But to be able to do that, you need a model that can handle very, very highly curved coastlines. So how have I changed it for gravel? I'm going to go through this. Essentially, everything is the same as this, mathematically. But what I've added in is the ability to resolve the height of the barrier, so the top of the barrier. So why is this important? Well, during a storm, the margin of safety can often come down to centimetres as to whether that gravel barrier can withhold a storm or not. So you need to be able to resolve the evolution to these sorts of scales, because it can have massive impacts as to whether, just for safety, because if the gravel barrier fails, you're going to get lots and lots of flooding. So you need to know what that gravel barrier is doing and how it's going to evolve. In terms of how I've developed it, I won't go into technical details too much, other than to say the topography of the model can vary through space but not through time. So it's kind of still making some of the inherent assumptions, but it's certainly an improvement on what previous models were doing. So how do you run a coastal evolution model? What data do you need? The first thing you need is a wave climate. So this is the study area for my first paper, is Dungeness on the southeast coast. Why Dungeness? It's a very large gravel beach and gravel barrier system. It's also operationally quite significant because there's a nuclear power station located at the shore. So what you have is wave climates all the way along the coastline. You can see here the majority of the waves are coming from the southwest. That's this direction. But you can also see that there's a northeasterly component too, coming from this direction. So what you need to be able to do is resolve both, because both are going to have some impact on the evolution, and previous research has shown that the evolution is predominantly governed by the southwesterlies. So what I've done is I can sample between the two components of the wave climate according to their prevalence. And I've also added in tide forcing as well, because you need to know how much of the barrier is can be mobilised at a given point, and a key component of that is the tide. What else have I added? I've also added Skew Surge. So to be able to predict into the future, you need to know what the water level's doing. You can't really do that terribly far in advance, because the models can only resolve sort of up to a week what the water level will do. So what we need is some sort of statistical method to be able to do this. So what we've got here, the black line is the astronomical tide. So that's what the water level is doing according to the positions of the sun and the moon, and it has no meteorological forcing in it whatsoever. So we can predict this many years in advance to sort of orders of centimetre accuracy. What we can't do is brilliantly well is resolve the water level with the impacts of the meteorological forcing and the weather. So what I need to calculate is the skew surge. So that's the difference between the peak water level with the impact of the weather and the peak astronomical tide, regardless of when the two happen. So they might be offset by a couple of hours, but what matters is the difference. And I've added this into the model by essentially looking at what the waves are and then sampling an appropriate skew surge for that given wave condition. So what am I trying to reproduce with this model? I'm trying to reproduce the coastal evolution at Dungeness over the last 5 to 10 years, but the Google Earth satellite imagery portrays this quite well. So what you would expect is you've got the southwesterly waves coming in here, so you would expect the sediment, the sand, gravel to move. It moves along around this coast. You can see here the difference between Dungeness in 1990 compared with 2017. That's this sediment being driven around the coastline here. Can my model reproduce that? Not terribly well at the moment, unfortunately. So what I've got here is the distance along the coastline. So starting from 0 is up here somewhere, moving along round the spit. Could be quite a few reasons for some of these errors. One is the stability. The other is some of the surveys that I'm trying to validate it against were often taken at different times of the year, and some of them don't look particularly convincing to me. So I'm worried about what I'm trying to validate my model against isn't a true representation of what the coastline's doing. Hopefully I can improve on this. What's coming next? So what we really need to be able to do to inform future flood risk management is to be able to say, right, this is what the coastline is going to look like in 10, 20 years. This is what's going to happen when you have a storm on that beach profile, and then you can work out what future impacts might be to inform economics and decision making. So what I'm going to do is chain Cove, my evolution model, to a storm impact model. So what the user can do is run Cove for say 5 or 10 years, stop it, get a barrier profile, so this would be the gravel barrier here, run your stormy conditions, so it might be a 1 in 200 year storm or a 1 in 50 year storm, and then use the outputs from that to feed that back into Cove and continue the cycle. So it's a way of being able to predict storm impacts on future beach profiles, because that's really, really critical to be able to do. There's lots of uncertainty in waves and tides, what they do during a storm, but actually the morphology and the shape of the beach barrier, whatever it might be, is also very, very important. And I've published work on that previously that shows that. What comes next? Okay, so once you've got the storm impact model and you know how much water is going to overtop the barrier and enter the floodplain, you can model the extent and depth of the flooding. Once you know the extent and the depth of the flooding, you can use depth damage curves to calculate an economic loss. So every single one of these grid cells, you look up the value. If it's a house and it's flooded to 1 metre, you've got a 10 metre square grid cell that's flooded to 1 metre, it's about £60,000. So what you can do is you can add up the total cost of an individual event. Once you've got the cost of an individual event and you've got a large ensemble of future scenarios, you can use what you call real options analysis. So I've compared it to cost benefit analysis because that's probably the most widely known one for sort of simple decision making, and I'm sure most of you have heard of it at some point. But real options analysis is starting to be used in climate change adaptation studies, and the key fundamental difference between the two really is the perspectives to the future. So cost benefit analysis uses one deterministic set of information. So this is what the sea level rise is going to do in the future, and we're going to make decisions appropriately. I need to wrap up. Whereas real options analysis is the future is uncertain, but we can explore the future with scenarios, so it incorporates and monetizes the uncertainty. Resolving longshore transport and overwash on spatially variable shore face topography and using multiple wave conditions moves beyond the assumptions which other meter scale coastal evolution models typically make. We can use that to rapidly project future evolution and use it to inform future management. I've gone well over time, I think.
Thank you.